Welcome to my video tutorial introducing acids and bases. At Key Stage 3 we characterised acids and alkalis by Robert Boyle's definitions. He suggested that acids were corrosive, had a sour taste and changed blue litmus paper to red. Whereas alkalis, which are soluble bases, had a soapy feeling and changed red litmus paper to blue. In 1884, Svante Arrhenius proposed salts dissociate when they dissolve in water to give charged particles called ions. He extended his idea by defining acids and bases as the following. An Arrhenius acid is any substance that ionises when dissolved in water to give the hydrogen ion, or a proton. At GCSE we could show that the hydrogen chloride gas, if you dissolve that in water, would give that hydrogen ion, or as we know at GCSE, the acidic ion, and the chloride ion. An Arrhenius base, on the other hand, is any substance that ionises when dissolved in water to give the hydroxide ions. And this can be shown in the reaction between sodium hydroxide dissolving or ionising in water. The Arrhenius theory helped to explain why acids have similar characteristics, since they all give off a proton or a hydrogen ion. It also explains why acids are neutralised by bases and vice versa. At GCSE we knew that this was the equation for neutralisation. It's a great theory to explain about acids and bases, but there were a few drawbacks to his theory. It can only classify substances when dissolved in water, since the definitions are based on the dissociation of compounds in water. It does not explain why some compounds such as HCl dissolve in water and some, such as CH4, do not, even though they both contain hydrogen. And finally, it only classifies bases if they contain hydroxide ions, and it can't explain why some compounds, such as Na2CO3 and NH3, have base-like characteristics even though they do not contain hydroxide ions. In 1923, Johannes Bronsted and Thomas Lowry individually proposed a set of new definitions for acids and bases, which are now known as either Bronsted-Lowry acids or Bronsted-Lowry bases, and at A-level there are definitions you will need to know. A Bronsted-Lowry acid is a substance that can donate a proton, or otherwise known as a proton donor. A Bronsted-Lowry base is a substance that can accept a proton, or a proton acceptor. Bronsted and Lowry's model of acids and bases gives rise to the concept of conjugate acid-base pairs. The first thing we have to do is to identify the pairs either side of the equilibrium. You can see that on this side, the HCl, it has one more hydrogen than its pair over on the other side of the equilibrium. If it's got an extra hydrogen or a proton, that means that in this pair, this is the acid and this will be its conjugate base. If we then have a look at the other pair with the water, you can see on this side of the equilibrium, the water has one less proton than its pair. This pair, by the way, is called the oxonium ion. I'll write that down in a second. Now, because this side has got one more proton, this side will be the acid, and therefore water on this side of the equilibrium would be acting as the base. So if we have a look now at Bronsted-Lowry's definitions of an acid and a base, an acid is a proton donor. Over here we have the acid, it has a proton, and it is actually donating it to the water. Over this side, a proton acceptor is classed as a base, while water here has accepted that proton, and so therefore water is the base. So let's take a look at another example between nitric acid and sulfuric acid. If we take the nitric acid here, we can spot its pair over the other side here. And with the sulfuric acid, we can see its pair is here. If we start off with the nitric acid, you can see on the left-hand side of the equilibrium there is one hydrogen, and over the other side of the equilibrium we have two. So it has one more hydrogen on the right-hand side, which says that this side must be the acid, and therefore this must be the base. It's strange to think that nitric acid is acting as a base in this reaction, but the base is a proton acceptor, and if you have a look on the right hand side, it has accepted a proton. Let's have a look at the sulfuric acid. So we can see on the left hand side it has two hydrogens, and on the right hand side of the equilibrium it has one. So therefore this side, on the left hand side, must be the acid, and an acid is a proton donor. It's going to donate that proton to the nitric. Therefore its conjugate base is over on the right hand side. Nitric acid has got one hydrogen ion or one proton to give away. Acids that have one proton to give away are classed as monoprotic. Other examples of monoprotic could be something like hydrochloric acid. It's got one hydrogen or one proton to give away. Sulfuric acid, on the other hand, has got two hydrogen ions, so therefore we call this diprotic. In acid-base equilibria, water can actually act as a proton donor, as an acid, or it can act as a proton acceptor, as a base. We call substances where they can act as either an acid or a base amphoteric substances. For this reaction with ammonia and water, you can see on either side with the pairs that ammonia has actually gained a proton. So we can say that this is the acid because it has an extra proton, and therefore the ammonia is acting as a base. It's acting as a proton acceptor. Water, on the other hand, if we look at the pairs, over this side it has one more hydrogen ion to its pair on the right hand side. So therefore it's acting as an acid on the left hand side because it's actually donating a proton. Therefore its pair is the conjugate base. However, let's have a look at water when it reacts with hydrochloric acid. So in terms of pairs, we can see that the hydrochloric acid has one extra proton than its pair, so therefore it's classed as the acid, and its pair is the conjugate base. And water, either side of the equilibrium, we can see on the right hand side it has one less proton than it does on the right hand side. So therefore this is the acid on the right hand side, and therefore it is acting as a base. At this point now you should be able to identify acid and base pairs in acid-base equilibria reactions. In my next video tutorial we'll be looking at pH of acids and the acid dissociation constant Ka. Thank you for watching.